On July 1, 2025, a survey telescope in Rio Hurtado, Chile, quietly logged a faint, moving smudge and changed the guest list of the solar system. The instrument belonged to ATLAS, the Asteroid Terrestrial Impact Last Alert System, and its report to the Minor Planet Center kicked off a global flurry of confirmations. Within days, astronomers agreed. The object was not just another native comet on a long, lazy ellipse. Its path was starkly hyperbolic, the unmistakable signature of something that does not live here. In other words, welcome 3IATLAS, the third confirmed interstellar visitor after the enigmatic ʻOumuamua and the icy comet-like 2I Borisov. One-liner. Not a tourist visa. This thing's on a one-way hyperbolic flight. What makes interstellar more than a sci-fi adjective is geometry. Picture a ball thrown so hard it beats Earth's gravity and never arcs back. Now scale that up to the sun. Most comets loop around the sun on stretched ovals, bound by its pull. A hyperbola is the mathematical escape shape, and 3IATLAS wears it proudly. Observatories on several continents traced its motion night after night and saw the same story. No matter how you tweak the numbers, the curve never closes. If orbits had social statuses, this one set its profile to single and not looking. Good evening, curious minds. Science doesn't need to shout to be fascinating. Sometimes it's best enjoyed the way you'd enjoy a late-night conversation, quietly, with a cup of tea, and maybe the soft hum of a fan in the background. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new as you drift toward sleep, consider subscribing. No pressure, only if you enjoy these calm journeys through the universe. Now, let's begin. The discovery itself is the kind of procedural thriller astronomers live for. ATLAS flagged the suspect motion, the Minor Planet Center circulated the coordinates, and a chorus of follow-ups poured in. Gemini, amateur arrays, and other survey cameras, pre-covery images, older photos where the comet had been hiding in plain sight, were pulled from archives, extending the observation arc and sharpening the track. It is like finding a stranger in a crowd and then noticing they photobombed last month's party picture too. Every additional dot on the sky tightened the solution until the calculated eccentricity, how unelliptical the path is, landed safely beyond the bound orbit threshold. Hyperbola confirmed, origins out there. Names tell the tale of that journey from suspicion to certainty. The object first wore a routine comet tag, C/2025N1, meaning it was catalogued in the second half of July and looked cometary. C says long-period comet, the kind you expect to come back after a very long nap. But once its trajectory proved unbound, the International Astronomical Union upgraded it to an I object, the special club for interstellar. The running number makes it the third of its kind, and ATLAS credits the survey that spotted it. The promotion from C to I is not a rebrand for hype. It is a precise way of saying the sun does not have this rock on a leash. Speed helps intuition. In practical terms, 3IATLAS is barreling through the inner solar system at tens of kilometers per second, fast enough that even Jupiter's large gravitational handshake cannot turn it into a regular. To humanize that, imagine crossing the distance from New York to Los Angeles in under 2 minutes, then keep that pace for months. Interstellar objects have what dynamicists call a hyperbolic excess velocity. The leftover speed after the sun's gravity has done its best to slow them down. That leftover is the passport stamp from another star's neighborhood. The third visitor label carries a lot of quiet weight. ʻOumuamua, the first, gave us a puzzle box, no visible coma, odd non-gravitational nudges, and a shape that launched 1,000 coffee debates. 2I Borisov, the second, looked reassuringly comet-like, with a classic fuzzy envelope and tail. 3IATLAS enters as a better-timed guest, caught earlier, with coordinated networks primed to pounce. That matters because the initial weeks of approach are where the orbit locks in and clues about composition begin to leak out. Think of it as meeting someone before the small talk calcifies. You can still ask real questions. The fieldwork behind those questions is part choreography, part endurance. Detecting faint motion near the crowded stellar backdrop of the Milky Way is like trying to track a drifting dandelion seed in a snow globe. Survey pipelines subtract out the fixed stars, stack exposures, and hunt for streaks that move just so from frame to frame. Once an alert goes out, the baton passes to bigger telescopes for deeper looks, to spectrographs for chemical fingerprints, and to orbit calculators who wring every drop of certainty out of pixel positions. Each team adds a tile, and the mosaic turns a rumor into a reliable ephemeris that anyone with a telescope can point to. If you are wondering whether this is dangerous, relax your shoulders. An interstellar trajectory does not imply a bullseye. In fact, the same speed that proves it is unbound also makes precision rendezvous unlikely. The track keeps it at a respectful remove from Earth, a drive-by, at the scale of astronomical units. Close enough for science, far enough to keep the disaster movie composers unemployed. Earth is basically a rock that won the cosmic lottery. But even lottery winners do not need to dodge every confetti cannon. There is also something quietly poetic about what an interstellar comet represents. It is a sample courier with no return address, a loose pebble from another planetary construction site tumbling through our foyer. Nature has mailed us a postcard, scrawled in dust and ice, and the postmark reads, "Elsewhere." That is why people who do this for a living got giddy on July 1st. It is not just a new object, it is a new comparison class, a chance to test whether our recipes for building worlds are local comfort food or a galactic staple. And yes, scientists celebrate with coffee rather than confetti, but the sentiment stands. We will dig into the name and the survey behind it next, because ʻAtlas turns out to be more than a mythological flex. It is a story about how a planet protects itself by watching the skies, and how vigilance for danger can also catch a once-in-a-generation visitor on the fly. Chapter 2, ʻAtlas. Before it became a headline attached to an interstellar visitor, Atlas was already a promise baked into its name, the Asteroid Terrestrial Impact Last Alert System. The last alert part is the key. This is a skywatch built for urgency, designed to sweep enormous swaths of darkness every clear night and raise a hand when something small, fast, and inconveniently close is on course to visit Earth. The original brief was practical and slightly nerve-wracking. Catch the couch-sized to house-sized intruders that bigger surveys might miss until the very last days or hours. In other words, Atlas is the neighborhood watch that never sleeps, logging patterns in the night and flagging anything that does not belong. One-liner, Atlas didn't shrug. It spotted a whole comet. Atlas earns that name with a very particular philosophy of hardware and cadence. Rather than a single giant telescope staring deep at a tiny keyhole of space, it relies on modest aperture, ultra-wide field instruments paired with sensitive, large-format detectors. Picture a set of vigilant eyes that can blink across the entire accessible sky multiple times per night. The field of view is so broad that it can tile the heavens like a high-speed paint roller, catching motion and sudden brightness changes that slower, narrower systems might step over. Depth is traded for coverage, and coverage is everything, when the target might be small, dim, and moving quickly against a backdrop of 100 billion distractions. Speed without smarts would be chaos, so the software is where the magic hardens into reliability. Each exposure is compared to reference images in a process called difference imaging. Subtract the past from the present, and most of the static universe cancels out. What remains are the variables and the movers: asteroids, comets, flares, glints, and yes, false alarms. The pipeline measures, filters, and scores these candidates in real time. Cosmic rays masquerading as things get tossed, internal reflections take a number and are dismissed. Objects that survive the gauntlet are linked across successive frames to form tracklets, short paths that prove consistent motion. The moment a candidate clears that bar, the system packages precise positions, brightness, and motion vectors, and ships them to the minor planet center, the clearinghouse that coordinates follow-up by the global community. That rapid handoff is not bureaucracy. It is choreography. A survey like Atlas all but assumes that others will join the dance within hours. Professional observatories can take deeper images to refine the path and measure color. Skilled amateurs, with their own fleet of impressive backyard hardware, can contribute time series data that fill in gaps. This is how you turn a spark into a bonfire of certainty. Lots of independent telescopes, different latitudes and longitudes, and an agreed-upon playbook for reporting. The last alert ethos is contagious in the good way, because it chases moving targets. Atlas optimizes not just for sky area, but for cadence, the beat at which it revisits the same region. A fast cadence is the enemy of missed opportunities. Imagine checking a crosswalk every few minutes instead of once an hour. Suddenly, the fleeting skateboarder is not invisible. In practical terms, Atlas will sweep, then sweep again, building up enough time-separated snapshots that motion pops out. That cadence also enables early light curve hints, the small variations in brightness that betray spin or activity. A rock that brightens from one pass to the next might be rotating, venting, or both. Either way, it is waving for attention. Why does an Earth protection survey end up bagging an interstellar comet? Because the same design that excels at nearby fast movers also happens to be excellent at noticing unusual motion against dense star fields. Interstellar objects do not behave like the usual suspects in the neighborhood. They arrive with odd inbound vectors and speeds that do not quite fit the gravitational music of the solar system. To a system trained to say, "Hey, that pattern is wrong," such outsiders are exactly the kind of wrong that rings every bell. It is a delightful side effect. The fire alarm also notices interesting weather. Names in astronomy are not just labels, they are breadcrumb trails. Upon first detection as a comet, the object received a provisional designation that encodes the year and half-month of discovery, plus a sequence tag. That cipher, C/2025N1, tells archivists and orbit computers where in the calendar it belongs and how it was classified at birth. The C marks it as a comet rather than an asteroid, with the expectation of a coma and tail. Later, when the trajectory analysis demonstrated that it was unbound to the Sun, the International Astronomical Union's scheme granted a different honorific, the sequential interstellar number and the discoverer's survey, thus 3IATLAS. The promotion is not cosmetic. It communicates physics at a glance. The ATLAS acronym itself is the kind of backronym that astronomers love, mythic resonance with functional accuracy. In Greek lore, Atlas holds up the heavens. In practice, Atlas holds up a nightly map of them and notices when the map changes. There is a reason these projects lean into memorable names. Public attention is not an afterthought. Awareness builds support, and support builds better instruments. When people can remember the Sentinel's name, they remember why we built it. None of this would matter without trust, and trust in survey data comes from relentless calibration. Wide-field systems wrestle with optical distortions, variable atmospheric conditions, and detector quirks. Atlas counters with careful flat fielding, astrometric solutions anchored to modern star catalogs, and quality control that promotes only the stoutest candidates. The result is a nightly feed that is both nimble and grounded, a rare combination in any scientific enterprise. It is easy to be fast. It is hard to be fast and right. So why Atlas? Because catching the unexpected requires an instrument that expects surprise. Because planetary defense is not a hypothetical poster in a conference hallway, but a living network that watches, shares, and improves. And because in the process of protecting our backyard, we sometimes glimpse a traveler from far beyond the fence, proof that vigilance can double as discovery. In the next chapter, we will trace where that traveler appears to have come from on the sky, following its inbound line like a thread pulled from the tapestry of the Milky Way. Chapter 3. From the Galactic South. If you were to pin a "You Are Here" sticker on the sky for 3IATLAS's inbound path, you would plant it near Sagittarius, where the Milky Way fattens into a bright, cloudy river of stars. That region is crowded. Astronomers call it the bulge, but galactic downtown captures the vibe. Our traveler's track, projected on the celestial sphere, points back toward that bustle, and slightly below the galactic midplane, a direction observers sometimes shorthand as the galactic south. One-liner, it came from the galactic downtown, not the suburbs. Why does that direction matter? Because directions encode stories about motion. On the face of it, interstellar debris should arrive from all over. Space is messy and big, but there is a subtle expectation rooted in kinematics. Imagine a calm pond dotted with tiny driftwood pieces. If you run across the surface, more wood will appear to come from the direction you are running into. In galactic terms, the sun is jogging through the local stellar flow toward the solar apex, a point in the constellation of Hercules. If interstellar objects were a tranquil sea relative to that flow, we would encounter more of them from the apex side, the way raindrops seem to smack your windshield from the front, even on a windless day. 3IATLAS appears to shrug at that trend. Its arrival vector leans toward Sagittarius, not toward the textbook apex corridor. There are several ways to understand this detour from the front windshield narrative. First, the interstellar ocean is not glassy. Nearby stars bob with their own random velocities, and the Milky Way's gravitational potential stirs everything slowly over time. The local standard of rest, our best guess at the average motion of matter near the sun, is a frame of convenience, not a cosmic law. A single object can easily inherit the peculiar motion of the star system that flung it free, so any distribution of arrival directions will have outliers, perhaps many. In statistics terms, we just drew a sample size of one from a very wide hat. Second, our measurements are made on a dome, not a flat map. When you chart a trajectory, you are projecting a three-dimensional motion onto a two-dimensional sky. The Milky Way's bulge happens to sit along a line of sight where star density is high, making the background rich and visually striking. That can create the impression of a special direction, when, dynamically, the object's actual velocity vector, through space, is only loosely aligned with that busy backdrop. To an experienced navigator, the scenery does not define the road, it just decorates it. Third, selection effects sneak in. Surveys are not equally sensitive at every hour or in every part of the sky. Seasonal weather, lunar glare, and instrument scheduling all modulate where we look. If your neighborhood watch spends more time on the street where most of the shops are, you will report more events there, even if mischief happens everywhere. The crowded regions near Sagittarius also draw lots of astrophotographers and follow-up observers who are already pointed that way for other projects, increasing the chance that a subtle mover is spotted sooner. Serendipity is a method uneven but effective. That said, the Sagittarius lean invites speculation, and speculation is useful when it is framed as a menu, not a verdict. One possibility is that 3IATLAS was born in a protoplanetary disk, orbiting a star that itself orbits the galaxy on a path oriented such that ejected debris naturally drifts through our neighborhood from the inner galaxy side, more often than random. Another is that the object's own ejection was recent in galactic terms, perhaps a close stellar encounter or giant planet migration kicked it loose with a velocity vector that happened to aim it along a line of sight that intersects the bulge. Over millions of years, these little directional biases get smeared by the galaxy's tidal field, but over shorter spans, they can remain coherent. Understanding the arrival vector also asks us to switch coordinate languages. Most of us are used to equatorial coordinates, the grid based on Earth's axis, and equator projected onto the sky. Galactic coordinates spin that grid so that latitude 0 follows the Milky Way's disk and longitude 0 points toward the center in Sagittarius. Describing 3IATLAS as arriving from the galactic south means its galactic latitude is negative. It is below the starry midline from our vantage. This change of frame is not mere jargon. Structures that look chaotic in one system can look tidy in another. An astronomer toggling between these frames is like a pilot flipping between airspeed and ground speed. Same flight, different truths. Why should you care beyond cartographic bragging rights? Because direction and speed together hint at origin. If, after careful modeling, the arrival bears little resemblance to the solar apex expectation, that strengthens the case that interstellar small bodies carry the fingerprints of their birth systems rather than some average neighborhood breeze. Each rock becomes a messenger from a specific elsewhere, not just a generic galactic background. That in turn shapes how we design future surveys and missions. If the sky is not isotropic in practice, we can weight search strategies toward the corridors that deliver the most messengers. There is also the romance of it. The center of our galaxy is hidden behind curtains of dust, but in infrared and radio, we know it is a place of dense star clusters, molecular clouds, and gravitational drama. Saying 3IATLAS hails from that direction does not mean it was minted near the black hole or carved from bulge rubble. Still, the symbolism is irresistible. A pebble from the general direction of the city center, passing briefly through our quieter spiral neighborhood street. The cosmos rarely hands us poetry. We make it from the data we get. In the next chapter, we will shelve the compass and pick up the stopwatch. We will ask the blunt question that orbits often answer best. How fast is fast? And what does that velocity tell us about the life this traveler led before it crossed our path? Chapter 4. How fast is fast? Speed, in astronomy, is less about bragging rights and more about biography. It tells you where an object has been, what pulled on it, and whether it intends to stay for dessert. For 3IATLAS, fast lands in the realm of tens of kilometers per second, with widely cited figures around 61 kilometers per second, depending on which frame you use and where it is on its plunge. One-liner, blink and you'll miss it. Cosmic drive-by, that quip is not hyperbole, it is kinematics with a sense of timing. A good first anchor is the neighborhood speed limit. Earth orbits the sun at about 30 kilometers per second. That is already zippy fast enough to circle our star in a year without spilling the oceans. Many long-period comets accelerate to higher speeds as they dive inward, but they remain loyal to the sun. Their paths are stretched loops. An interstellar visitor arrives with extra energy in its pocket. Think of the sun's gravity as a hill. Bound comets roll down and back up to the same side. 3IATLAS starts with enough momentum to crest the hill and keep going. The technical way to say that is it carries a hyperbolic excess velocity, the speed it would still have far from the sun after all the gravitational braking is over. That leftover is the signature of elsewhere. As it falls toward the sun, the comet trades altitude for speed, racing faster the nearer it gets. The mathematics behind that trade is usually written as an equation, but the story is simple. The deeper the gravitational well, the more you accelerate, the more you climb out, the more you decelerate. Near perihelion, the point of closest approach, it reaches its top speed for the entire passage. For 3IATLAS, that sprint happens in late October 2025. After the turn, the numbers unwind in reverse, the same shape of speed curve, only in the opposite direction. If you could mark its velocity on a coaster at your local cafe, the inbound and outbound sides would mirror. 61 kilometers per second is a mouthful, so let us translate. That is roughly 136,000 miles per hour, fast enough to cross a continent between sips of coffee. Compared to human hardware, it is swifter than Voyager's cruise, and in the league of our fastest heliocentric travelers, though still leaving bragging rights to the sun-skimming probes that dive deep by design. Crucially, this is not a steady cruise set by a throttle. It is a ballet of vectors: heliocentric speed, geocentric speed, and line-of-sight components that swell and shrink as the geometry evolves. Depending on the date, an observer on Earth may measure a slightly different number than a theoretician quoting the sun-centered speed. Fast does not just mean gone soon, it leaves fingerprints on the data. If you are imaging, long exposures smear the object into a dash while stars stay crisp, unless you deliberately track at the comet's rate and let the stars trail instead. That choice is not aesthetic, it is survival. Faint details in the surrounding coma vanish if motion blur washes them out. Observers plan shorter exposures, more frames, and careful stacking to keep up with the sprint. The comet is not being coy. Your detector just needs to breathe between strides. Speed also pushes and pulls on spectra. When gas around the nucleus glows in narrow lines, those wavelengths shift a little due to the Doppler effect, shorter when it approaches, longer when it recedes. At these velocities, the shifts are small fractions of a percent. But for modern spectrographs, that is plenty. It helps separate the comet's fingerprint from the night sky's own emissions and from terrestrial glow. The trick is to remember that Doppler tells you about the line-of-sight slice of the velocity. You need the full three-dimensional picture to understand the orbit. Another consequence of speed is jurisdiction. Gravitational capture is dramatically unlikely because capture requires shedding energy, and space is short on brakes. A close pass by a planet could, in principle, siphon some speed through a slingshot. But at these high approach velocities, the odds of hitting the right corridor are not worth betting the observatory on. Encounters that are common for slow-bound comets, gentle tugs that reshape a loop, become drive-bys with little lasting imprint. When the guest is interstellar, you can wave, you cannot grab the bumper. Timing matters too, because the peak speed and brightness concentrate around perihelion. The best window for high-resolution data is a compressed season. Late October is not just a calendar note, it is a statement about the steepness of the speed curve. Weeks can make the difference between a target approachable in modest instruments and a ghost for only the largest mirrors. After perihelion, as the energy balance flips, the comet decelerates and fades. It will not dawdle. Observing campaigns that move at the speed of committee do not fare well against objects that move at the speed of math. It is tempting to turn this into a contest. Fastest comet, fastest flyby. But that misses the point. In dynamics, speed is a witness. It testifies that the object is unbound, that it was cast out from a different gravitational family, and that it is passing through ours with opinions of its own. If it feels theatrical to call this a cosmic drive-by, it is only because the script is written by Newton and played on a stage 100 astronomical units wide. Next, we will lean into the practical question you were probably already thinking. How close does this get? And what does fast imply for safety and visibility from our safe little rock? Chapter 5. Safe, but not sorry. Relax your shoulders. 3IATLAS is not a doomsday delivery. The numbers draw a comfortable moat. Its closest approach to Earth is on the order of 270 million kilometers, about 1.8 astronomical units. That is nearly twice the Earth-Sun distance. Perihelion, the point where it skims closest to the Sun, sits near 1.4 astronomical units, just inside the track of Mars. In orbital geometry terms, we are watching from the balcony, not the splash zone. One-liner, close enough to wave, not close enough to panic. How do you know an object is harmless when it still looks like a dot? The answer is a chain of increasingly sharp position measurements and the mathematics of uncertainty. Early on, every orbit solution comes wrapped in an error ellipse, a region on the celestial sphere where the object is most likely to be found next. Night after night, telescopes tag the comet again. The ellipse shrinks, and the computed path firms up. If you propagate that path forward, and it misses Earth by a huge margin, you can go ahead and finish your coffee. For 3IATLAS, that margin is not a rounding error. It is the difference between a hallway and an ocean. Impact risk is reported on some famous color scales, but those were engineered for objects that actually cross near Earth's orbit. The Torino scale gives the public-friendly traffic light rating. The Palermo scale speaks to specialists by comparing risk to background impact odds. A body sailing past at roughly 1.8 astronomical units is, in plain language, not applicable to these alarms. You do not call the fire department for fog outside the city limits. It is still logged, modeled, and archived, just not in the queue that keeps planetary defense folks up at night. Distance has physics baked in. Even if Earth and the comet were in the same segment of space, gravitational focusing, our planet's mild ability to bend incoming paths, only matters when an object is already flirting with a collision corridor. From hundreds of millions of kilometers away, Earth's tug amounts to a polite nod. There are no resonant keyholes or narrow gravitational gateways to worry about on a pass this wide. The hills and valleys of orbital mechanics that sometimes shepherd asteroids toward trouble are simply too far from the route 3IATLAS is taking. You might ask whether the track could drift as outgassing changes the push on the nucleus. That is a good instinct. Jets of vapor and dust can impart small non-gravitational nudges to comets. The key is scale. Those subtle accelerations are interesting for fine-tuning an ephemeris, but they will not teleport an object across astronomical units. Think of a canoe catching a gust. Yes, it steers, but it will not leap to another lake. Navigators will model these forces to improve pointing for telescopes. They will not revise safe to surprise. Speaking of pointing, the generous distance also telegraphs the observational personality of this visitor. Wide berth means low apparent motion across the sky, compared to a close Earth grazer, which simplifies tracking for small observatories. It also means the comet's apparent size remains modest. We will resolve structure with big glass and long exposures rather than dramatic naked-eye displays. Safety and spectacle tend to be anti-correlated. The closest calls make the loudest scenery. In that sense, a sleepy visual shows our luck is working. Communication matters because the internet treats every cosmic pebble like a cliffhanger. The rule of thumb is boring but powerful. The more separation in astronomical units, the more separation from anxiety. When official channels say no risk, they are not hand-waving. They are leaning on datasets that are public, reproducible, and checked by more than one team. The workflow is collaborative by design. Surveys report, the Minor Planet Center curates, independent orbit computers cross-check, and anyone with the coordinates and a telescope can test the solutions. Panic does not survive contact with transparency. Could a planet other than Earth meddle with the path? Not meaningfully at these ranges. Jupiter is the heavyweight in our system, and its influence can sculpt the loops of bound comets over long periods. But a fast interstellar passerby that never threads the giant planet's neighborhood will not pick up a dramatic deflection. A quick metaphor. Jupiter is the bouncer who matters at the door. If you never enter the club, you do not get bounced. Radar, our best close-range measuring stick for near-Earth asteroids, will sit this one out. Even powerful planetary radars require targets that come within a few tens of millions of kilometers to return a useful echo. At 1.8 astronomical units, 3IATLAS is a whisper you cannot ping. That is fine. Optical and infrared measurements are made for this regime. They map the track, estimate activity, and monitor how the coma evolves as the sun warms the surface, all from a safe, civilized distance. There is a philosophical bonus too. Safety lets science breathe. When observers do not need to triage potential hazard work, they can schedule deep exposures, spectroscopy, and coordinated campaigns without the adrenaline tax of an imminent flyby. The slow drama of a distant pass is ideal for teaching, for public events, and for careful method building. It is hard to explain orbital dynamics when the object is sprinting through a keyhole. It is easy when you can point, night after night, and show the same faint wanderer marching predictably across the stars. Safe, but not sorry, also means we can afford curiosity. We can ask patient questions about dust production, jet geometry, and how the coma brightens with solar distance, knowing the comet will not demand emergency headlines. The result is a dataset tuned for understanding rather than alarm. the sort of evidence that improves our models for the next interstellar passerby, whatever direction it chooses and however flashy its entrance. Next, let us pivot from distance to appearance. How bright will 3IATLAS get? When will it peak? And what can a determined observer actually see through glass and pixels when the headlines have folded? Chapter 6. How bright will it get? Let us set expectations the way astronomers set alarms, conservatively. For 3IATLAS, the best current guesses put the peak brightness around magnitude 11 to 12. Solid quarry for larger amateur telescopes, but invisible to the naked eye in all but the most unrealistic conditions. One-liner, not a sky billboard, more like a cosmic whisper. That whisper matters, because with comets, the value is not only how loud they speak, but what story the hush is telling. Magnitudes sound like a strange currency because they are. The scale runs backwards. Bigger numbers mean fainter objects, and each step is a large change, not a polite nudge. If street lamps had magnitudes, your porch light might be magnitude -5 and a candle down the block magnitude 5. The candle is not 5 times fainter. It is drastically so. When we say 11 to 12, we are in the domain where binoculars shrug and small telescopes start to earn their keep. You will not walk outside, glance up, and see a silver sword stretched across the sky. You will aim carefully, dark adapt your eyes, and coax a smudge from the background. That smudge has its own weather. Early images already reveal a faint coma, a soft glow surrounding the unseen nucleus, hinting that sunlight is heating the surface enough to sublimate ices and loft dust. Tail development is a process, not a jump cut. First come the short, tentative extensions, as dust grains are pushed by sunlight and gas ions are swept along magnetic field lines in the solar wind. With time and more heat, the dust component can broaden into a fan, while the ion tail often sharpens into a narrow, filamentary spike, pointing almost straight away from the sun. Each night writes a new paragraph on a moving page. Brightness predictions live on 3 moving targets: distance from the sun, distance from Earth, and how efficiently the comet turns sunlight into glow. The first 2 are geometry. They change smoothly and predictably. The last one is the joker in the deck. Comets vary wildly in how much dust they shed, how reflective that dust is, and how gas production ramps with warming. Some are stingy and dark, throwing off only a thin veil. Others are florists with a glitter budget. A small dusty outburst might bump the total light for days. A quiet spell might drop it. This is why every forecast comes with a shrug and a pencil eraser. There is a 4th ingredient that observers feel in their bones: the angle of sunlight, known as the phase angle. When the sun, the comet, and you line up in a way that puts the comet at a crescent phase, sunlight scatters off grains in a manner that can either flatter or flatten the brightness. At very small phase angles, close to a straight backlight, some comets show an opposition boost, where dust reflects more efficiently. At larger angles, the same dust can look drabber. None of this demands arithmetic to understand. It is the same reason a dusty shelf glows at sunset, but looks dull at noon. If you are chasing the whisper through an eyepiece, aperture and sky quality are the real gatekeepers. Under pristine rural skies, an 8-inch telescope can make a magnitude 11 smear stand out with averted vision, using the more sensitive part of your retina by looking slightly to the side. Under urban light domes, even a 12-inch tube may struggle, unless the coma expands and spreads its light more generously. Tilters can help in photographs, isolating specific emissions in the gas. But visually, the best filter is a dark, moonless night and patience. Your eyes are lab instruments if you let them be. Photographers face a different quirk: integrated brightness versus surface brightness. The total light from the coma might sum to magnitude 11, but if it is spread over a large patch, each square arc minute is dim. A compact galaxy of the same magnitude can look snappy. A diffuse comet can look like someone exhaled on the lens. This is why observers swap notes that sound paradoxical. It is bright, but it is faint. Both are true. The flux is there, the surface glow is shy. As the tail matures, composition quietly sculpts its look. Larger dust grains scatter sunlight broadly and tend to produce wider, softer fans that keep shining even as activity dips. Very fine grains and gas ions create needle-like structures that can be startlingly straight, but are often too dim to see visually. Long exposures can reveal these subtleties, especially when aligned to the comet's motion and stacked to lift the signal from the background. The result is a kind of time-lapse portrait of physics: sunlight pushing, plasma streaming, gravity tugging at the larger flakes as they lag behind the nucleus. A word of caution for those translating images into expectations at the eyepiece. Processing is an art. Contrast stretching can make a faint tail leap from the screen, while the real-time view remains modest. That is not deception. It is the point of long exposure. But human eyes only integrate light for a fraction of a second. What a camera adds across many minutes, your retina cannot. When you plan a session, let the photos inspire you without promising you the same fireworks. If there is a wild card, it is the potential for brief outbursts, sudden releases of gas and dust as a crust fractures or a patch of fresh ice rotates into sunlight. These can lift the magnitude by a notch and sharpen structures for a night or two before settling. Outbursts are not guaranteed. They are just part of the comet's temperament. Think of them as the object clearing its throat on stage. So yes, the forecast calls for a quiet visitor. A magnitude 11 to 12, glow with evolving structure for those willing to do the work. The reward is not spectacle, but subtlety. The pleasure of watching a small body warm, breathe, and leave a tracery across the night. In the next chapter, we will explore why some of the most striking pictures of this traveler look like a rainbow brushstroke across a star field, and why the colors are telling you more about the camera than the comet. Chapter 7. That peculiar rainbow streak. If you saw the viral image of 3IATLAS looking like a neon brushstroke across a star-crowded sky, you probably wondered if the comet was moonlighting as a disco light. Tempting, but no. The rainbow is an artifact of how the picture was made, not a confession about the comet's taste in outfits. One-liner, prism chic, brought to you by the instrument, not the comet's fashion sense. Here is the play-by-play. The Gemini Observatory's multi-object spectrograph, GMOS, does many things well, and one of its crowd pleasers is color imaging through a set of filters. Think of filters as carefully carved slices of the visible spectrum: bluish, greenish, reddish, each one admitting a different band of wavelengths. To build a color picture, the telescope takes separate exposures through several filters in sequence, then software maps those exposures to red, green, and blue channels and combines them. If the target sits still between filter shots, you get a normal-looking scene. But our target was not sitting still. It was a fast-moving interstellar visitor, weaving through a dense field of background stars. Now recall, the stars are effectively fixed dots at these exposure times, while the comet crawls a tiny but measurable amount between each filter. When you stack the images aligning on the stars line up perfectly in all three color layers and look white or neutral. But the comet's position shifts from layer to layer. Result, the comet appears as a short red segment, then a slightly offset green segment, then a blue segment stitched together into a rainbow dash. It is the astrophotographic equivalent of a flipbook, where the character moves while the scenery does not. The color trail measures time as much as it does light. This is not a glitch. It is a choice. You can align a multi-filter composite on the stars and let the moving target split into colors, or you can align on the comet and let the stars stretch into color-separated streaks. Both tell the truth, just different truths. Aligning on the stars makes for a familiar, postcard-ready Milky Way with a multicolored comet track. Aligning on the comet gives you a clean, gray-white coma and tail, but turns the background into a gallery of red, green, blue tridents, one for each star. Neither is photoshopped in the pejorative sense. Both are responsible data reductions, with different alignments. So why do the star-packed fields around Sagittarius make the effect pop? Density and contrast. A background riddled with points holds still and gives the eye a firm reference frame, which makes any moving element stand out, especially when that motion gets painted in primary colors. The rainbow becomes a highlighter for motion in a crowded classroom of static dots. If you took the same multi-filter sequence against a sparse field, the color displacement would be subtler and less shareable, but it would be the same physics. Could the atmosphere be guilty here? Atmospheric dispersion. Earth's air, acting like a weak prism, can indeed split colors slightly, stretching blue lower and red higher when targets are near the horizon. In the Gemini image, that effect is small compared to the much larger separation caused by time and motion between filters. If atmospheric dispersion were the main culprit, stars would sprout color fringes in the same direction, not just the moving comet. In the GMOS rainbow, the stars keep their dignity. It is the comet that walks through the palette. Notice something else. The colors in the trail are broad, band-like, and cleanly segmented. Real cometary color, when you catch it, is more subtle, gentle tints from reflected sunlight and faint emissions from gases, smeared together in the coma. Instrumental rainbows look like traffic lights in sequence. Natural colors look like whispers stacked on whispers. In technical terms, the GMOS filters, often Sloan-like GG, R-Rhine, I, etc., carve the spectrum into hefty slices. Assign GG to blue, R-Rhine to red, I to a warm channel, and you get that tidy stoplight palette in the composite. Nature rarely color codes so politely. The processing pipeline matters too. Color balancing a tricolor image involves decisions: how to scale each channel, how to map them to display colors, how aggressively to stretch contrast. Those choices do not invent features, but they can emphasize some and soften others. When you are aiming for an illustrative result that shows motion, leaning into saturated channel mapping makes sense. The rainbow line is not telling you the comet has turned into a cosmic parrot. It is telling you the filter wheel ticked over while the comet kept cruising. A good way to sanity check all this is to look for the opposite alignment. Find a version where the reduction aligns on the comet, and the background stars become prismatic streaks. Each star's red, green, and blue exposures peeled apart along the direction of the comet's motion. Same data, different anchor point. The symmetry is your proof that this is geometry plus timing, not an extraterrestrial light show. Science loves invariance, and the invariant here is that only one of these populations moves, the comet. There is also a quiet methodological win baked into that candy stripe. It encodes the comet's apparent rate and direction of motion across the sky. During the sequence, measure the spacing between the colored segments, check the timestamps for each filter exposure, and you have a tidy estimate of angular speed and position angle. A picture that wows the internet can double as a ruler for orbit refinements. Form and function, wearing the same jacket. If you are wondering what the comet would look like to the human eye at the eyepiece, subtract the choreography of colored filters and subtract the long integration. You would see a low contrast, mostly gray fuzz with perhaps a hint of tint under very dark skies, and a large telescope. Our eyes are terrible spectrometers. Cameras make rainbows. Retinas make approximations. All this tees up a natural next step. If the rainbow streak is instrumental, what genuine colors, if any, belong to 3IATLAS itself? In the next chapter, we will chase the real hues that sometimes arise in Comete Comets, what molecules paint them, and how to tell honest chemistry from photographic theater. Chapter 8. Green Glow Mysteries. If you have seen photos hinting that 3IATLAS wears a touch of green, you have met one of cometary science's favorite optical party tricks. The color is not paint, it is chemistry done in sunlight. A glow coaxed out of fragile molecules that only exist for moments in the vacuum around a warming nucleus. Reports of a greenish hue match what many solar system comets show. When activity ramps, and the likely culprit is diatomic carbon, C2 excited by solar ultraviolet light. One-liner, space mint, now with extra interstellar flavor. The recipe goes like this. As the surface warms, ice is in and just under the skin of the nucleus sublimate, dragging with them a zoo of small molecules and dust grains. Some of those molecules are parents, carrying carbon in forms like acetylene or ethane. Bathed in ultraviolet photons, they fall apart. Among the fast, delicate daughters born in that photodissociation is C2, a simple pair of carbon atoms that cannot survive long. While it exists, sunlight kicks its electrons into higher energy states. When those electrons relax, the molecule radiates at a set of bright bands clustered in the green part of the spectrum called the swan bands. To a camera and occasionally to patient eyes at a big enough telescope that paints the inner coma with a green wash. There is a second act to this story, why the green does not usually stretch down the tail. The same ultraviolet light that excites C2 also destroys it, with typical lifetimes measured in minutes to hours, depending on distance from the sun. By the time gas has flowed outward and solar wind has started to carve tails, much of the C2 has been broken into even smaller fragments that do not glow the same way. Dust, being stubbornly solid, reflects sunlight and looks neutral or slightly warm. Ionized gases fluoresce mostly in blues. The result is a green-tinged inner halo tapering into a grey dust fan and a bluish, needle-like ion tail, an ombre produced by physics rather than a stylist. Because 3IATLAS is not native, the green is more than an aesthetic flourish. It is a diagnostic. Spectrographs can break that light into lines and bands, measuring ratios like C2 to CN, cyanogen, or C3. Those ratios are the chemical accent of a comet, not unique to an individual, but telling you something about the pantry it came from. In solar system comets, the distribution of these ratios correlates with families and formation zones. Finding the same patterns or striking deviations in an interstellar visitor tests whether planet-forming disks elsewhere cook with similar ingredients. If C2 is abundant relative to CN, you have one set of implications for how carbon was locked up in the ices. If it is scarce, you have another. Either way, you are learning about a nursery we cannot visit. There is nuance in the green itself. Not all greens are created equal. A handful of comets display a vivid apple glow in small telescopes. Others remain stubbornly grey, even when spectra say the molecules are there. Two things conspire to hide the tint: surface brightness and dilution. If gas production is modest and the coma expands rapidly, the C2 emission spreads thin and the surface brightness drops below what your retina can distinguish. Photographs with long exposures and tight filters will still pull it out, but the visual impression stays subtle. This is not the comet being coy, it is optics plus biology. Human eyes are worse than cameras at detecting color in the dark. Add to that the phase angle, the geometry of sun, comet, and observer, which changes how dust scatters light and can either flatter or mute the green glow. Backscattered dust can look brighter and slightly warmer, washing out delicate emission. Side-lit dust can step back a little, giving the gas a chance to show off. None of this changes the underlying chemistry. It is the lighting designer twiddling dimmers while the actors do the same lines. Misattribution also lurks in the background. You may have heard of a green oxygen line at 557 nanometers, famous for auroras. In comets, atomic oxygen does emit in green, but it typically arises from the breakup of water and carbon dioxide farther from the nucleus and seldom dominates the inner coma's color. The tidy banded structure around the green in comet spectra points firmly to C2. Put differently, oxygen adds a highlight, carbon writes the headline. For 3IATLAS, the real scientific juice will come from how the green evolves. As the comet approaches and recedes from the sun, production rates change, and so do the lifetimes of fragile molecules. Observers will measure how the C2 bands strengthen, how far from the nucleus they remain detectable, and how they compare to companion features, like the violet CN band. If the green spikes early and then stalls, perhaps the outer layers are rich in carbon-bearing volatiles that get spent quickly. If it grows steadily, maybe the reservoir is deeper or more evenly mixed. Either way, time series spectroscopy turns color into a timeline. There is even the possibility, if the data are generous, of peaking at isotopes. Ratios such as 1/√C leave faint fingerprints in the band structure. In solar system comets, those ratios tend to cluster near values measured in meteorites and planetary atmospheres. If an interstellar comet showed a meaningful offset, it would hint that its parent system's chemistry unfolded under slightly different rules. Different starting cloud, different radiation field, different temperature history. That is a high bar for data, but the carrot is big. So when you hear green comet, resist the urge to picture a neon snowball. Think of a thin shell of gas lit from within by physics that happens in seconds, written in lines that instruments read like sheet music. For 3/ATLAS, that sheet music plays an old tune, swan bands we know well, performed by a visiting orchestra. Familiar notes, unfamiliar provenance. That is what makes it enticing. Not uniqueness for its own sake, but comparability with a twist. Next, we will trade color for scale and ask the question everyone secretly wants answered. How big is the thing making all this fuss? And how do you size a nucleus that hides behind its own breath? Chapter 9. What size are we talking? Astronomers have a favorite riddle disguised as a photograph. How big is the thing hiding in the glow? For 3IATLAS, the answer currently lives inside a roomy range, somewhere between a few hundred meters across and a few kilometers. The spread is not indecision, it is physics being uncooperative. A comet's nucleus is the introvert at its own party, wrapped in a light-scattering crowd of gas and dust that overpowers the host. One-liner, is it a pebble in a puff jacket or a boulder in a mist? The first temptation is to take how bright the object looks and convert that into a diameter. If only it were that simple. A bare rock reflects sunlight according to its size and its surface reflectivity. Make it darker, and you need more rock to get the same brightness. Make it lighter, and you can shrink the rock. Cometary surfaces are generally gloomy. Think charcoal more than snowball. But we rarely know exactly how gloomy. Now add the coma, which is a swarm of dust grains acting like a billion tiny mirrors. Much of what you measure through the telescope is the cloud, not the core. Measuring the nucleus from that is like estimating the size of a person by the glow of a fog bank. Observers fight back with models that try to separate a sharp, star-like core from the diffuse haze. They compare the comet's light profile to the telescope's point spread function, the signature of a true point source, then ask how much extra fuzz must be present to match what the camera recorded. Subtract the modeled fuzz, and what remains is a guess at the nucleus's own contribution. It is a bit like unmixing paint after you have stirred it, and the uncertainties are honest. If the coma brightens or fades between exposures, if jets make it asymmetric, or if the seeing blurs the seen, the subtraction leaves fingerprints. Thermal infrared offers another path. Sunlight warms the nucleus, which then glows faintly in heat, rather than reflected light. Dust also glows, but not in exactly the same way. With the right wavelengths, instruments can favor the nucleus's warmth over the coma's glitter. The trade, again, is assumptions. You need to guess how efficiently the surface re-radiates heat and how rough it is, because a lumpy, porous world warms and cools differently from a smooth slab. Change those beaming assumptions, and the diameter you infer slides around. The good news is that, as the comet brightens, the signal climbs, and multiple wavelengths help pin the answer. Light curves add personality to the size question. As a lumpy nucleus spins, its cross-section presented to us changes, and the total brightness can bob in a repeating pattern. If that bob survives after you account for coma variations, you can estimate how elongated the body might be and set boundaries on its minimum size. A small, wildly elongated object can mimic the brightness of a larger, rounder one. The amplitude of the wobble is a hint. The period is a clue. The coma is the heckler. Patience and dense sampling help separate the stand-up routine from the background laughter. Occultations, moments when the comet crosses in front of a distant star, are the gold standard for size, because they can draw a silhouette. Predicting them requires an exquisitely accurate orbit and a bit of luck, and catching them demands observers along the thin path the shadow drags across Earth. With interstellar guests, the geometry window is tight and the motion brisk, but if the stars align, literally, even a short blink can carve a hard upper limit on diameter. You do not need to see the nucleus, you just need to watch a star briefly stop existing. Dust production metrics with jargon like AVRO appear in reports and can be mistaken as size stand-ins. They are not. They tell you how much scattering material is present near the nucleus, not how large the rock itself is. A small but hyperactive nucleus can look brighter than a big but lazy one because the dust swarm dominates the show. That is why size estimates, especially early ones, come with generous error bars and notes like assuming a typical albedo. The word typical is doing a heroic amount of work. High-resolution imaging will help as the apparition matures. Adaptive optics on large ground-based telescopes can sharpen the inner coma and reduce the blending that plagues small instruments. Space telescopes dodge atmospheric blur altogether. With enough angular resolution, the innermost glow can be measured more cleanly, which trims the uncertainty on how much of the light budget belongs to the nucleus. Pair those images with thermal data in the mid-infrared, and you get a cross-check. The same object constrained by two different yardsticks. Because 3IATLAS is not from here, comparisons will inevitably orbit around our only other interstellar size benchmarks. The caution is to remember that each visitor arrives with its own activity level, surface properties, and illumination geometry. Using a past guest's wardrobe measurements to tailor the new suit is risky. Better to let the data for this traveler speak and accept that hundreds of meters to a few kilometers is an honest state of play until the instruments earn the right to be picky. The most likely trajectory for the estimates is narrowing by attrition. As more spectra arrive, the albedo guess becomes less of a shrug. As more images resolve the inner region, coma subtraction gets less acrobatic. As more light curve points pile up, rotational modulation is either seen and modeled or ruled too small to matter. Every one of those steps trims the wings of the error bars. The endgame is not a single magic number, but a range that everyone can agree on without crossing fingers. So, pebble in a puff jacket or boulder in a mist. Today, the safe answer is that either wardrobe could fit, give the telescopes time, and the tailor will stop pinning and start stitching. Next, we will pivot from silhouette to fingerprint and ask what the spectrum says about what this thing is made of and how that chemistry compares to the recipes we know from our own neighborhood. Chapter 10, Composition Clues. When you cannot grab a sample jar, you let the light do the lab work. Composition for 3IATLAS will be read off the spectrum, those barcode patterns of bright and dark, where atoms and molecules show up like suspects at a lineup. Instruments across the visible and infrared are already sniffing for volatiles and dust, and the goal is simple in spirit, if not in execution. Compare the fingerprints to what we know from homegrown comets, and see where the match breaks. One-liner, space CSI, matching fingerprints from another star system. Start with the gas. Sunlight and warmth crack open ices near the surface, releasing vapor that glows at characteristic wavelengths. In the optical, familiar tracers include CN in the violet, along with bands from assorted carbon chains. Slide to the near-infrared, and you find heavyweight clues, water's overtone features, carbon monoxide's tight lines, carbon dioxide's broad signatures, and a menagerie of organics such as methanol and formaldehyde. Each family tells a different chapter of the comet's thermal history. Carbon monoxide survives in the coldest storage. Water waits for milder heat, Methanol and friends sketch in the chemistry that happened on dust grains long before any star was born. Ratios between these species are the real gossip. CO to water, for instance, or methanol to water, because they are less about how bright the comet looks today and more about how its ices were stocked. Enter the specialists. Webb's NIR spec and MIRI are built for this kind of sleuthing, separating crowded infrared lines so cleanly that even faint species can be tallied. Hubble, with its ultraviolet reach, can chase products like OH that trace back to water, especially when the inner coma is too small for ground telescopes to resolve cleanly. From the ground, high-resolution spectrographs slice the optical and near IR into razor-thin channels, making it possible to disentangle overlapping features and pick out weak emissions parked next to stronger ones. The trick is coordination. Catch the same object with multiple instruments, close in time, and you can build a chemical ledger rather than a stack of disconnected receipts. Dust gets its own interrogation. In reflected sunlight, the continuum can slope from neutral to increasingly red with wavelength. The spectral slope, a proxy for grain size and surface coatings. In the mid-infrared, dust stops reflecting and starts glowing, and mineral features leap out. Silicates sing near 10 and 18 microns, letting you gauge the mix of glassy and crystalline grains. The presence of crystalline olivine or pyroxene implies heating at some point in the material's past. A purely amorphous signature whispers pristine and cold. If a visitor from another system shows an unusual blend, say a strong crystalline note where most comets are shy, that is a clue that its nursery mixed and heated dust differently. Polarimetry adds another angle, literally. Sunlight scattered by asymmetric grains becomes polarized, and the degree and orientation of that polarization change with the phase angle. Plot that curve, and you have a handle on grain porosity and size distribution. Comets from our own backyard cluster along a few familiar polarization tracks. If 3IATLAS traces a curve that bends away from those families, we will suspect its dust is either fluffier, more compact, or coated with compounds less common here. Think of it as learning about a beach by how glare plays on its sand. Then there are the isotopes, the rarest and noisiest prizes. Slight shifts in line positions betray whether carbon is mostly the 12-mass variety, or if 13 makes a noticeable showing. And similar games can be played with nitrogen and hydrogen. In our system, many comets carry a deuterium to hydrogen ratio in water that is higher than Earth's oceans. It is one reason we think icy asteroids, not typical comets, did the bulk of our hydrating. If an interstellar comet delivered a markedly different DH, or an odd nitrogen ratio, it would suggest its parent cloud saw a different temperature regime or radiation bath. Caveat engraved in stone. Extracting these tiny differences demands exquisite signal and careful modeling. The risk of fooling yourself is non-trivial, and sober teams wear their error bars like life jackets. Non-gravitational forces, the tiny rockets produced by asymmetric outgassing, also carry indirect chemical hints. If CO dominates, activity can light up at larger solar distances, where water remains sluggish, and the direction of the thrust can shift as seasonal illumination moves across the nucleus. Track those nudges over weeks and you sketch a map of vent locations and dominant volatiles without ever seeing a jet. Dynamics becomes forensics. Which propellant is steering the ship? All of this works better if you watch the score change with time. A snapshot tells you what on one night. A series tells you how and when. Comets grow and relax. Jets rotate into view, and the sun's angle changes the energy budget. A gas that lags in response might be locked beneath a crust and only escapes after heat soaks deeper. A species that spikes at dawn on the nucleus could be sourced from a field of fresher ice. Coordinated campaigns, space and ground, optical through mid-IR, turn the light curve into a chemical weather report. And then comes comparison. Place 3IATLAS on the same scatter plots we use for local comets. CO versus water, methanol versus water, dust to gas ratios, silicate feature strengths, polarization at a given phase angle. If it lands among the familiar clusters, we learn that chemistry in planet-forming disks may be stubbornly generic. If it perches on the margins or pioneers a new island, we gain permission to rethink how ingredients get sorted and processed beyond our spiral arm. Both outcomes are valuable. Either way, the data will push a model somewhere. None of these measurements will be perfect, and some will disagree at first pass. That is normal. The point is not to declare alien or ordinary in one dramatic press release, but to accumulate enough independent constraints that the picture converges. Science is happiest when multiple imperfect methods point to the same conclusion from different directions. Next, we take a step back in time. How old might this traveler be? And what does old even mean for a fragment that has wandered star to star before stumbling into our sun's light? Chapter 11. Old. Maybe really old. Age, for a comet, is not a birthday candle count. It is a portfolio of scars. When some researchers suggest 3IATLAS could predate our solar system by billions of years, they are not reading a label on the nucleus. They are inferring from physics that operates on galactic timescales. If borne out, we are looking at a primordial sample, material assembled in a protoplanetary disk around some other star, long before our own sun lit up. One-liner, grandparent comet dropping by to tell origin stories. How do you even begin to date a wanderer without a return address? Start with context. Small icy bodies are factory seconds from the era of planet building. In any young stellar system, gravitational jostling flings a fraction of those leftovers outward. Most park in distant reservoirs. A few win the slingshot lottery and are ejected to interstellar space. Once loose, their orbits cease to be about a single star and become about the galaxy. Slow diffusion through changing gravitational fields, punctuated by the occasional nudge from passing stars and giant molecular clouds. The journey is patient, hundreds of millions to billions of years long. Mere youth would be the surprising claim. Clocks exist, but they are subtle. One is chemistry that should not survive heat. Volatiles like carbon monoxide, nitrogen, and certain noble gases prefer deep freeze. If spectra show generous amounts of these fragile species, even after gentle solar warming, it argues that the object spent the overwhelming majority of its life in cryogenic darkness, shielded from multiple close passes to any star. That favors an ejection early in its native system's history, followed by a long, cold exile. Youthful travelers tend to carry warm processing signatures. Ancient drifters keep the freezer burn. Another clock is written by cosmic rays. High-energy particles pepper interstellar objects continuously, driving slow-motion chemistry. Over millions of years, irradiation can redden and darken surfaces, produce complex organics, and weld thin skins that are less volatile than the interior. A kind of crunchy glaze on a soft center. If early observations hint at very dark, reddened dust and a tendency to form a crust that needs only mild heating to crack, that is consistent with lengthy exposure to interstellar space. It is not a date stamped in years, but it leans toward old soul. Isotopes whisper about ancestry and sometimes age. Ratios such as deuterium to hydrogen in water or nitrogen-15 to nitrogen-14 in nitriles are imprinted by temperatures and radiation fields in the birth cloud. If those ratios differ from solar system norms in ways that match what we expect of very early cold chemistry, the case strengthens for a primordial origin. No single number will say older than 4.5 billion, but a pattern across several elements can rule out later, warmer reprocessing, and point to assembly under ancient, pristine conditions. Think of it as hearing an accent from a region that has not existed for a long time. Texture matters too. Crystalline silicates require heating above hundreds of degrees. Amorphous silicates do not. The proportion between them, read off mid-infrared spectra, can index how much thermal cycling a body endured. In our system, outward transport of high-temperature grains into cold zones muddied the story. Yet comets still carry a mix. For an interstellar visitor, The balance will hint whether its natal disk performed a similar dance of radial mixing. A low crystalline fraction would tilt toward a disk that never warmed the source region. A higher fraction would imply recycling through hot zones before incorporation. Either way, we get a timestamp of sorts, not a date, but a thermal biography that is more likely old than freshly minted. Dynamics offers corroboration. Objects ejected late from a mature planetary system have a better chance of carrying signatures of multiple close stellar flybys or planet-planet upheavals. Those histories tend to leave specific biases in speed and spin states. Ejections during the chaotic youth of a system, while giant planets are still migrating, are more numerous and set most interstellar debris on its billion-year walkabout. The galaxy acts as a blender. The longer you are in it, the more randomized your motion relative to any local standard. If 3IATLAS's kinematics look thoroughly mixed rather than freshly minted from a particular moving group, ancient wanderer becomes the default hypothesis. Can we ever move from maybe really old to yes, really? In a lab, we would count daughter products of short-lived radionuclides or measure cosmic ray tracks in mineral lattices. Through telescopes, we triangulate. Time series spectroscopy can track how quickly heat penetrates and releases volatiles. Slow, deep responses hint at a layered structure consistent with long irradiation and little previous heating. Polarimetry across phase angles can reveal whether the dust is exceedingly porous, a hallmark of aggregates that have never been compacted by repeated close passes to stars. High-resolution imaging of jet behavior can show whether venting prefers fresh fractures, old crust, or uniformly porous surfaces. Simple youth is less likely to create a strong crust. Caution sits in the front row. Some signatures of age mimic signatures of environment. A young object ejected into interstellar space could accumulate a radiation crust faster than you expect if its surface composition is particularly sensitive. A genuinely ancient body could have its crust reset by a single close brush with a star long ago. That is why multiple independent lines of evidence matter. When chemistry, texture, kinematics, and activity history all hum the same tune, confidence climbs. Why the fuss about age at all? Because early material is a message from an epoch we cannot witness directly. Our solar system's preface is mostly erased by later heating and mixing. An interstellar fragment that formed before our planets did could encode a snapshot of pre-solar chemistry, the distribution of organics, the abundance of primordial ices, the degree of isotopic fractionation, written in a hand the galaxy taught to many disks, not just ours. If you want to know whether life's starting kit is standard issue or boutique, grandparent comets are excellent interviewees. If 3IATLAS truly carries that kind of antiquity, then every photon we steal from its coma is a page from an old manual. We may not translate every paragraph this time, but we will learn which sections to copy for the next visitor. And that sets up the question at the heart of this series. Why do interstellar comets matter so much for planetary science? Next, we pull the camera back and make the case for why these brief encounters can rewrite big chapters in how worlds are made. Chapter 12, Why Interstellar Matters. If the solar system is one kitchen, interstellar comets are takeout from across town. They arrive unannounced, still warm, and force us to ask whether everyone follows the same recipe or whether our menu is an acquired taste. That is the scientific juice. Interstellar bodies let us test whether planet-forming rules are local quirks or galactic habits. One-liner, universal cookbook. Does everyone else also oversalt with carbon monoxide? Comets are time capsules, but local ones were packed in our own pantry. Their ices and dust reflect the temperatures, pressures, and radiation fields that prevailed in the sun's natal disk. Interstellar visitors, by contrast, were assembled in somebody else's disk, perhaps cooler, perhaps dustier, perhaps stirred more vigorously by infant giant planets. When we compare their gases and grains to ours, we are doing comparative planetology at the ingredient level. If the volatiles align, similar water to carbon monoxide ratios, familiar organics, we gain confidence that disks everywhere synthesize the same starter kit. If they diverge, we learn where the universal ends and the how special begins. The most consequential questions live at the wet end of the spectrum. How are water, carbon monoxide, and carbon dioxide partitioned in the outer disk? That balance sets the positions of snow lines where each compound freezes, and those boundaries, in turn, shape what growing planets can accrete. A disk that condenses carbon monoxide efficiently farther out, for instance, may produce planetesimals loaded with hypervolatile ices that later seed young atmospheres with carbon compounds. If multiple interstellar comets lean rich in such volatiles relative to water, we would suspect that many planetary systems start with carbon-heavy outer zones. If they are stingy, we recalibrate our expectations for early atmospheres elsewhere. Either way, this is not trivia. It is climate control for newborn worlds. Dust tells a parallel story. The size, porosity, and mineral makeup of grains tune how quickly they clump, drift inward, and feed fledgling planets. Crystalline silicates, grains that have been annealed at high temperatures, indicate substantial thermal processing and large-scale mixing. Amorphous silicates suggest gentler, colder assembly. If visiting comets consistently showcase a different crystalline to amorphous balance than ours, we learn that some disks keep the oven hotter or stir the pot more. That cascades into how quickly pebbles grow, how soon giant planets can form, and whether those giants migrate to sculpt the remaining disk. The consequences echo from micron-sized dust to the final architecture of planetary systems. Organic chemistry may be the most tantalizing cross-check. Complex organics, methanol, formaldehyde, maybe even faint hints of more elaborate chains arise on icy grain surfaces, long before any planets exist. If the relative strengths of those features in interstellar comets cluster around solar system-like values, it suggests that prebiotic chemistry is not a boutique phenomenon, but a robust outcome of cold interstellar physics. If they do not, we have homework. Perhaps ultraviolet fields vary enough between star-forming regions to tilt the synthesis. Perhaps the timing of ice mantle growth shifts the product list. Either way, the stakes feel large because these are the molecules that can seed atmospheres and, in generous circumstances, feed biology. To be clear, comets delivering life's molecules is plausible but debated. What is solid is that they deliver raw carbon chemistry in bulk. Interstellar debris also stress tests our ideas about how planetesimals are launched into space. In young systems, gravitational scuffles between giant planets eject vast numbers of small bodies. The rate and timing of those ejections depend on planet masses, disk lifetimes, and migration histories. If we log many interstellar comets and notice patterns in their speeds, spin states, or typical compositions, we can invert the problem, read the census to infer how other systems rearrange themselves. It is a statistical game. Today, we are arguing from a small sample, but even a handful of well-characterized visitors can prune whole forests of theoretical possibilities. Selection effects matter, and acknowledging them is part of the point. Our telescopes discover what they are good at discovering. Fainter, slower, less active interstellar objects may slip past undetected, biasing early samples toward gassy, dust-friendly types. Recognizing that tilt lets us design smarter surveys, deeper searches, wider cadence coverage, and better sensitivity to oddballs. The next decade's instruments will push hard in that direction, turning "we got lucky" into "we are prepared." That is why every interstellar visitor, even a modest one, is a calibration point for the search strategy itself. Another payoff is methodological. Interstellar comets force coordination across wavelengths and facilities, welding together techniques that are sometimes siloed. Optical emission bands, infrared vibrational lines, and thermal dust features are different dialects of the same story. Reading them side by side sharpens models, reduces degeneracies, and builds a toolkit we can apply to faint disks around young stars where we cannot isolate single comets. Ironically, a flyby pebble in our sky can improve how we read the unresolved glow of faraway nurseries. There is a philosophical dividend too. A single visiting fragment can validate the idea that materials cycle across the galaxy, born in a cold cloud, assembled in a disk, kicked loose by planetary billiards, and eventually drifting into another star's light. That cycle blurs the line between their stuff and our stuff. It hints that the starting conditions for making planets are not parochial, they are shared, traded, and constantly remixed. If that sounds poetic, it is because the data give us permission to be a little grand. Skepticism should ride shotgun. With only a few interstellar objects in hand, we cannot declare a cosmic norm. Outliers may be loud. Confidence will come from repetition. New visitors, new spectra, new patterns that either clump where theory predicts or force revisions. The promise is not that any single comet will settle arguments, but that a series of them will teach us where universality ends and individuality begins. Next, we pivot from why to how we capitalize when a serendipitous traveler shows up. How do we marshal spacecraft already in the solar system to grab bonus angles and data with minimal fuss? Chapter 13, Spacecraft Piggyback. Space is big, but our toolbox is now everywhere. Circling Mars, threading past Jupiter, riding heliocentric orbits that skim the solar wind. When a brief visitor like 3IATLAS drops in, we do not need a bespoke chaperone to learn something useful. We can piggyback on spacecraft already out there, bending their daily routines just enough to snag angles no telescope on Earth can offer. One-liner. No dedicated mission. We're phoning it in from 3 planets. What makes this worth the choreography is geometry. Most Earth-based observations see the comet from roughly the same side of the dance floor. A camera at Mars or a probe closer to the Sun can look from a very different direction, delivering phase angles, the Sun-Comet observer angle that Earth can never reach during this apparition. At small phase angles, you sample a backlit halo. At large ones, you catch forward scattered light, when dust grains act like tiny headlights and the comet's coma brightens disproportionately. That steep forward scatter boost is priceless for constraining grain sizes and textures. It is as if a passing car suddenly turned on its high beams and revealed the shape of the fog. Mars orbiters are natural first call partners. They have sensitive cameras, spectrometers in the ultraviolet, through infrared, and they can slew with precision. A Martian vantage gives a parallax baseline millions of kilometers wide, which tightens the orbit solution when combined with Earth views. It also unlocks phase angles that Earth cannot access at the same time. An ultraviolet spectrograph at Mars, for instance, can measure emissions from fragments of water or carbon dioxide, while Earth-based instruments tackle the visible bands. Cross-calibrating those measurements from 2 angles helps separate what is chemistry from what is lighting. Even better, a time series from 2 worlds can reveal rotation-linked jet behavior. Without waiting a full spin, one observer sees late afternoon on the nucleus, while the other sees morning, letting us map local time effects on activity. Jupiter's neighborhood brings complementary perks, although Jupiter-orbiting spacecraft are not comet chasers by design. Their cameras and spectrometers sometimes have windows where pointing off the planet is safe. If the geometry lines up, they can snag phase angles close to 90 degrees or more, which are tough to obtain from Earth at the same moment. Those oblique views amplify polarization signals, how scattered sunlight becomes partially aligned in one direction. Polarization curves are exquisitely sensitive to dust porosity and shape. A single high-phase data point from far away can anchor a whole model. In short, a quick glance from Jupiter's zip code can tell us whether the dust is more like compact sand or airy snowflakes. The most dramatic piggybacks, though, often come from the fleet of solar-orbiting sentinels. Coronagraphs designed to study the Sun's outer atmosphere regularly catch sun-grazing comets. Wide-field heliospheric imagers watch faint structures drifting through the solar wind. These instruments already track tiny, moving, faint things against a messy background, perfect training for an interstellar visitor. If 3IATLAS crosses their fields, we can watch how the tail responds to changes in the solar magnetic field in near real time, not merely infer those changes after the fact. A heliospheric imager can record the large-scale dust fan and ion tail over days without the interruptions that bedevil night-bound facilities on Earth. No clouds, no sunrise, no competing time zones. Think of it as switching from still photography to a time-lapse documentary. Coordinating any of this is part science, part air traffic control. First, ephemerides have to be accurate and uploaded to each mission's planning system. No small task when the target is faint and hustling. Pointing constraints then gate the wish list. Some spacecraft must keep their solar arrays facing the sun within tight tolerances. Others must protect sensitive star trackers from bright fields. The safest line of sight may be a narrow corridor. Data volume is another break. Deep exposures generate big files, and downlink schedules are negotiated weeks in advance. A single bonus image may need to hitch a ride on a carefully budgeted communications window, elbowing for space among weather maps of Mars or magnetometer sweeps of the solar wind. But even a modest dataset pays dividends. A handful of images at extreme phase angles can lock down the phase function, the curve that relates brightness to viewing geometry, turning a hand-wavy assumption into a measured property. A short ultraviolet sequence from a second vantage can triangulate the distribution of specific gases in the inner coma, showing whether jets are narrow fans or broad outflows. Combined with Earth-based spectra, that 2- or 3-point view lets us infer whether a specific volatile is lofted everywhere or localized to a rotating sector. The result is a kind of low-budget tomography, not a picture of the nucleus itself, but a map of its breathing. Occasionally, we can piggyback on instruments that were never intended to image comets at all. Dust analyzers on heliophysics missions can log tiny impacts from grains crossing their orbits. The direction and speed of those hits, tied to the comet's ephemeris, disentangle which particles are truly cometary and which belong to the background interplanetary dust. Even a sparse set of impacts constrains the size distribution of grains escaping the coma, information that is notoriously slippery to extract from brightness alone. Meanwhile, plasma instruments can track the arrival of pickup ions, freshly ionized atoms swept into the solar wind, signaling how the comet's gaseous outflow interacts with the heliosphere on scales far larger than any telescope's field of view. There is also a calibration bonus. Spacecraft far from Earth see different scattered light backgrounds, different instrumental stray light patterns, and different cosmic ray environments. Getting the same comet through these different cameras stress tests our reduction pipelines. If two instruments with wildly different systematics recover the same phase, function, or polarization trend, confidence climbs. In the long run, that makes us better at reading faint, moving targets that never get near a planet or within range of Earth's night. None of this replaces a dedicated flyby. A purpose-built mission would sample the coma in situ, weigh grains, sniff gases at the source, and image the nucleus up close. But piggybacks are the art of the possible. Quick pivots, opportunistic geometry, and science pulled from the gaps between primary objectives. The price is small. The payoff is leverage across angles we would otherwise miss. Think of it as citizen science, but the citizens are robots orbiting other worlds. Next up, we will leave the mission planning spreadsheets and wade into the public square. How to keep the story tethered to data when rumors, hype, and alien ship headlines try to outrun the photons. Chapter 14. Public hype versus hard data. The moment a new interstellar visitor trends, the internet splits into two camps. It's aliens and it's Photoshop. Meanwhile, astronomers are over here counting photons and propagating ephemerides like accountants with better screensavers. Viral claims pop up: self-lit comet, evasive maneuvers, metallic glint with intent. and agencies calmly reply that the object behaves like a comet, obeying the same gravity the rest of us do. One-liner: if it's an alien ship, it forgot the turn signal and the user manual. Let us talk about how science filters extraordinary claims without turning into a buzzkill. The first sieve is prediction. A real orbit, derived from multiple nights of precise astrometry, predicts where the object will appear next, down to arc-seconds on the sky. If observers at different longitudes and latitudes can point there and reliably find the same fuzz waddling along the same path, that beats any dramatic single-frame anomaly. Hype rarely comes with a tomorrow test. Data lives on it. Next is reproducibility. Claims that depend on one camera, one filter, or one lucky exposure are legally required to sit in the corner until someone else can reproduce them. We saw it brighten by 2 magnitudes in 10 minutes. Becomes interesting only when a second, independent instrument confirms the jump, while others, watching different wavelengths, catch correlated changes. A lone image with no calibration frames, no timestamps, and a creative color stretch is not a discovery, it is a mood. Instrumentation quirks are the hype artist's favorite accomplices. Internal reflections can draw ghostly shapes offset from bright stars. Cosmic rays can scribble neon streaks across a single exposure. Aggressive noise reduction can invent ripples where none exist. Teams fight these gremlins with flats, darks, and bias frames, then cross-check suspect frames against adjacent ones, a feature that walks with the telescope's orientation or vanishes when you rotate the instrument, is not attached to the comet. It is attached to optics and software. Pareidolia, our talent for seeing faces in toast, does the rest. Self-luminosity is a perennial rumor, so let us pin it down. Comets shine primarily by reflecting sunlight and by weak emission from excited gas. If something were generating its own power, like a flashlight, you would expect odd phase behavior, brightness unchanged regardless of viewing angle, or light curves that ignore solar distance. Observers test that by tracking the photometry over weeks and comparing the trend to well-understood phase functions and heliocentric distance. If the curve follows the playbook, the self-lit theory gets benched. Spoiler, it follows the playbook. Another crowd pleaser is course correction. The comet zigzagged, someone says, pointing at a stacked image with a broken line. In reality, stacking short exposures without compensating for the object's acceleration can produce a segmented trail. Each subframe aligns on stars, so the moving target appears in a slightly different place. Align the stack on the comet, and the maneuver evaporates. When real non-gravitational forces are present, jets acting like weak thrusters, they show up as smooth, modelable deviations from a purely gravitational trajectory, consistent across datasets. Nature does small nudges. Conspiracy does abrupt turns between JPEGs. Agencies and observatories try to meet the moment with radical transparency, public ephemerides, open light curves, quick-look spectra, even raw frames. They also add context that social feeds skip, error bars, observing geometry, and instrumental limits. We think comes with a confidence interval, not a drum solo. It is not that scientists dislike drama, they just prefer the kind that survives a second act. There is a communication trick worth learning. Uncertainty is not indecision. Early in an apparition, you will hear phrases like provisional orbit, tentative detection, and consistent with. That is not hedging. It is labeling the confidence level. Honestly, so that when claims escalate, you know who is counting and who is guessing. Think of it as the difference between a weather forecast and a wish. If someone selling a wild interpretation cannot tell you their assumptions, priors, or error budget, they are not doing science, they are doing improv. Social media, for its part, rewards spectacle over method. A sharp image with saturated colors and a spicy caption travels. A careful plot comparing phase-corrected magnitudes dies in committee. That is why science communicators translate. They show the pretty picture and then annotate it. Here is why the rainbow streaks appear. Here is why the tail kinks when the solar wind shifts. Here is how we know the nucleus did not bank left. Good outreach is not scolding. It is demystifying the magic trick so you can enjoy the real wonder. Red flags for the curious. Beware solitary images with no acquisition details. Watch for claims that ignore basic geometry. It brightened while moving farther from the sun without phase correction. Be skeptical of screenshots with compression artifacts promoted as surface texture, and treat any single witness account that fails a "can someone else elsewhere see it too?" check as provisional entertainment. Also, note the incentives. Clicks are a currency, so are citations. One of these is easier to mint. Finally, remember that the alien hypothesis is not forbidden. It is simply expensive in evidence. Extraordinary claims are welcome to the table when they bring extraordinary, multi-instrument, multi-observer, time-consistent data. Until then, the comet category, with its sublimation physics, dust scatter, and gravity, fits the facts while spending far fewer assumptions. Occam's broom sweeps glitter pretty efficiently. If hype is popcorn, hard data is protein. Enjoy the show, but let the numbers do the heavy lifting. Next, we pivot from the rumor mill to the searchlight. How a faint, fast mover got spotted against the noisiest backdrop in the sky, and why detection, this time, was a small miracle of cadence and cleverness. Chapter 15. How we found it, against the odds. Galactic center season is gorgeous and inconvenient. The sky near Sagittarius bristles with stars, dark lanes, and stray nebulae. Beauty that doubles as camouflage. Against that backdrop, a faint, slightly fuzzy speck, sliding a few arc-seconds per minute, is the very definition of hard mode. Finding 3IATLAS there took a toolbox built for chaos, precise plate solving to nail where each pixel lives on the sky, and stacking strategies that turn a handful of noisy frames into a confession. One-liner. Finding a dim fuzzy in the Milky Way glare is like spotting a gray cat in fog. Start with the crowd problem. In sparse fields, an automated pipeline can compare tonight's image to a reference, subtract the stars, and catalog what is new or moving. In the bulge, subtraction gets messy. Minute differences in focus, seeing, and atmospheric shimmer make every bright star sprout residuals when you try to remove it. Little donuts, ripples, and ringing that masquerade as real objects. Now add unresolved star clusters and filamentary dust that change the background from pixel to pixel. The result is a minefield of false positives before you even start asking what moved. Plate solving is the map that keeps you from getting lost. The software identifies asterisms, constellations inside the constellation, and matches them to star catalogs, solving for distortion, rotation, and scale, so that every pixel understands its celestial address. In crowded regions, the trick is not just matching, but discriminating. Many random triangles of stars look alike. Solvers lean on robust algorithms that can tolerate outliers, saturated cores, and blended sources. Once the plate is solved, you can anchor successive images to the same world coordinate system with sub-pixel precision. That is the difference between stacking into clarity and stacking into mush. Even with a perfect map, single exposures are stingy. Trailing losses nibble away at signal-to-noise when the object moves during the exposure, smearing its light across multiple pixels. The cure is shorter frames and more of them, but that raises read noise and multiplies data volume. Enter track and stack. Shift each frame by the predicted motion of the target before adding them together. Stars obligingly become short streaks. The moving speck becomes a point. If your motion guess is even a little off, the target stays fuzzy. If you guess right, it pops. That pop is not just aesthetics. It is the statistical boost that lifts it above the ocean of bulge glitter. Pros have pipelines. Advanced amateurs have ingenuity. Many backyard teams now use synthetic tracking, a GPU-accelerated cousin of track and stack. Instead of betting on a single motion rate, they brute force a grid of rates and position angles across dozens or hundreds of frames, co-adding along each hypothetical path. Most paths produce noise. The true path produces a compact source that rises above the noise like a buoy. It is computationally expensive, but so is everything interesting. And it is precisely the kind of search that shines when confusion from star fields drowns simpler methods. Point spread function, PSF matching, is another quiet hero. Subtraction works best when the reference image and the new image blur stars in the same way. In practice, seeing never cooperates. Algorithms such as kernel regression morph one PSF into another before subtracting, shrinking those annoying rings around bright stars. Do it well, and the subtraction image becomes a nearly blank canvas with only movers and variables left as brushstrokes. Do it poorly, and you get a Jackson Pollock of false alerts. There is also the art of not fooling yourself. Cosmic ray hits tend to show up in only one frame. Hot pixels never move. Internal reflections pivot around bright stars as the pointing changes. Pipelines flag anything that fails as seen in N frames, with consistent motion and flux test. Human vetting, ironically, is still part of the loop. Experienced observers glance at candidates and instantly spot the tells. A ghost perfectly mirrored across a bright star, a moving dot that coincides with a known bad column, a smart-looking streak whose segments line up with the cadence of the filter wheel rather than the clock. Calibration is the scaffolding under all this. Flats tame dust motes and vignetting so that gradients do not masquerade as Comanet. Bias and dark frames keep the detector's gremlins from drawing spurious objects. Good astrometry demands good timing, so observatories obsess over clock discipline. A timestamp off by seconds can ruin a tracklet when an object is crawling through the field. In crowded regions, dithering, nudging the telescope a few pixels between exposures, helps average over bad pixels and builds a cleaner master frame for subtraction and stacking. Then there is the problem of victory looking like failure. A line on the stars and the moving comet becomes a color-split dash in multi-filter sequences. A line on the comet and the stars become tri-colored streaks. Both are correct, but automated vetters trained on round star heuristics might throw out precisely the frames that prove motion. Teams tuned for the bulge loosen those priors, let the stars trail, require coherence in the comet's centroid across the stack, and demand that a candidate also emerges when you change the binning or the aperture. Redundancy beats any single clever trick. Advanced amateurs brought serious leverage. Fast optics with large sensors, low-noise CMOS cameras, and software like Tycho Tracker, Astrometrica, and custom Python notebooks let home observatories behave like mini-surveys. A typical playbook: shoot a burst of 30 to 60-second frames, plate solve and register them. Synthetic track across a range of rates whispered by early ephemerides, and then push promising stacks through photometry to confirm that the signal behaves like a moving object rather than a fluctuating background knot. Cross-checks against current catalogs of variables and known asteroids clear the suspects list before a report is filed. Reporting is choreography in its own right. A credible discovery or confirmation bundle includes calibrated images, world coordinate headers, measured positions with uncertainties, the photometric method, and the assumed motion used for stacking. Against a star swamp, trust me, does not cut it. The Minor Planet Center ingests these data, links them to prior nights, and if the math holds, spits out an updated solution that sharpens tomorrow's hunt for everyone else. It is relay racing with photons. So yes, the glamour shot belongs on posters, but the detection was a triumph of logistics and math. Plate solving told us where, stacking told us what, careful subtraction told us what not to believe. The grey cat walked through fog, and we caught the tail flick. Next, we will trade the Discovery Saga for practical sky time, when and how to aim your own gear, if you want to log 3IATLAS from your backyard without sacrificing sleep or sanity. Chapter 16, Observing It Yourself. This is the do-it-yourself chapter, boots on the grass, eyepiece at the ready, and a polite pact with the mosquitoes. 3IATLAS is no naked eye spectacle. It rewards preparation and calm technique. Think of it as a quiet guest who speaks softly but says interesting things if you lean in. One-liner, astrophotography's cardio, track, stack, and don't breathe on the mount. Start by choosing the right tool for the job. A larger amateur telescope, an 8-inch class or above, gives you a cushion against faintness, especially under suburban skies. Reflectors need clean collimation. Refractors need a dew shield that actually shields. Pair the scope with a sturdy equatorial mount that does not flinch when a breeze asks rude questions. Wobbly tripods are the enemy. So are loose clutches and cables that snag at the worst moment. Balance the rig slightly east-heavy so the drive gears stay engaged rather than chattering. Your future self will thank you at 2 in the morning. Eyepiece choice is about context. Start wide to locate the field, then bump to medium power to tease out the glow. Averted vision, the trick of looking a little to the side, can make the difference between maybe and there it is. If you sketch, log the size of the fuzzy spot relative to nearby field stars and note any asymmetry. Comets are living things in slow motion. Your sketch becomes a time capsule when you revisit the field a night later and see the blob shifted and subtly reshaped. For images, the watchword is steadiness. You want crisp stars and a cooperative mount so the comet's slight motion is what you notice, not your guiding tantrums. Keep cables dressed, lock down every thumbscrew, and set your guiding exposure long enough to average out seeing jitter, but short enough to catch corrections before the mount drifts. If your software supports it, use a rate that follows the comet's drift rather than the standard sidereal pace. Even a partial match cuts smearing. When in doubt, err on the side of shorter sub-exposures and more of them. Faint targets repay patience better than heroics. Focus is not a one-time checkbox. Temperature drops pull optics out of tune, so refocus periodically. A focusing mask helps you nail it without guesswork, and focusing on a star close to your target reduces the different corner of the sky problem. If you are using a camera lens, tape the focus ring after you nail the star. One casual bump can exile sharpness for the session. Timing is everything, and the calendar is kind. The most comfortable windows are after sunset, from July through September, with the comet climbing into view as twilight fades. Week to week, check how high it will sit an hour after dusk. Altitude beats all other variables except clouds. Transparency matters more than textbook excellent seeing. You want a dry, clear night rather than a steady, soupy one. The moon is the world's brightest noise source. Schedule around its glare whenever possible, and use a simple sky brightness meter or your experienced eyeballs to decide whether tonight is photography or just look and log. Field planning saves time. Bring a printed chart or a tablet with a red screen mode so your dark adaptation survives contact with your enthusiasm. Star hopping to a rich Milky Way field can be confusing. Mark 2 bright anchor stars and learn the short hop from the second anchor to the target field. If you image, frame a distinctive asterism in the corner as a reference, you will thank yourself when you revisit the spot to measure motion the next night. Keep a checklist on paper: power on, polar align, focus, acquire, start guiding, take a test exposure, verify, start sequence. Checklists are boring until the one time you forget a step and spend an hour solving a problem called cap still on. Thermals are quiet saboteurs. Let mirrors and lenses equalize before you start serious work. Heat plumes inside a tube turn faint comb into mush. Dew is the other villain. Use a heater strip on optics and a gentle fan on the secondary, if your scope allows it. Keep a microfiber cloth for emergencies and never wipe a wet optic. Let the heater do the work while you sip a warm beverage and contemplate the universe's expansion and your patience. Camera settings? Aim for well-behaved histograms, not hero shots. ISO or gain should land your sky background away from the left wall without approaching saturation on field stars. Sub-exposure length is a compromise between the comet's drift and your mount's honesty. 30 to 120 seconds is a sane starting region for many rigs. Take calibration frames that match the night, fresh darks for the temperature, flats for the exact optical train, and bias or dark flats to taste. Your processing tomorrow will be measured in gratitude per frame. Visual observers can still contribute. Record the comet's brightness by comparing it to nearby stars using out-of-focus disks, a classic technique that softens everything to blobs and makes honest estimates easier. Jot the estimated diameter of the coma in arc minutes using your eyepiece's known field. Note any hint of a tail and its direction relative to the nearest bright star. Repeat a few nights later. Congratulations, you're doing time domain science without a single pixel. If you want to get fancy, coordinate. Two observers a few hundred kilometers apart can measure the comet's position the same evening and compare notes. Even small differences help refine the track. A group can plan a cadence so that someone always has the object near their local meridian, maximizing altitude and minimizing atmospheric muck. Post your results where other observers gather. Faint targets are a team sport, and your data point might be the one that closes a gap. Finally, practice kindness to your future self. Label your files with date and time in universal time. Include the field center in the name, and keep a written log. The next day, you will not remember whether IMG 7342 was the good one. Also, do not breathe on the mount. Seriously, leaning on the tripod mid-exposure is the amateur astronomy version of sneezing on a birthday cake. With a little discipline, this quiet target turns into a satisfying ritual. A faint glow inching across a star tapestry, night after night, like a second hand in a cosmic clock. In the next chapter, we will ask what happens after the clock strikes perihelion, whether this traveler keeps its poise, flares, or sheds a few pieces on the way out. Chapter 17. After the sun skim. Perihelion is not a finish line. It is a stress test. As 3IATLAS rounds its closest approach to the sun, the thermal tide runs deepest into the nucleus, and what was a controlled simmer, inbound, can flip into a boil on the way out. Sublimation does not switch off when the comet turns the corner. Heat lags, layers that were merely warming before closest approach, now cross their thresholds, and latent ices wake up late to the party. That is why post-perihelion months can be dramatic. Outbursts, fresh jets, and in edgy cases, pieces deciding they liked being neighbors less than they thought. One-liner, a quick sun kiss, then Irish goodbye to the whole solar system. Outbursts first. These are sudden spikes in brightness, driven by a patch of surface, failing catastrophically. A crust fractures, pressure vents, and gas drags dust outward in a plume. The telltale signature is a rapid brightening, followed by a slow fade as the ejected cloud expands and thins. On the outbound leg, these events can be more likely, because fractures propagated during the inbound heat-up finally reach critical length after the thermal wave penetrates a bit deeper. Think of it as popcorn physics. The kernel pops not at first warmth, but when heat reaches the core. Fragmentation is the louder cousin. If internal stresses exceed the feeble cohesion of a rubble pile nucleus, shear planes can separate, and a lumpy monolith becomes a small family. Whether that happens depends on a tug-of-war among thermal stress, volatile pressure, and rotation. Outgassing is a sneaky spin coach. Jets act like thrusters, altering rotation rates and sometimes pushing a world from leisurely tumble toward the brink where centrifugal forces assist the split. If the breakup is gentle, fragments drift apart at walking speed, each growing its own coma. If not, dust swarms saturate the neighborhood, and the light curve looks like a fireworks finale. We saw a textbook case of outbound fragility in the second interstellar visitor, 2I Borisov, which shed material more eagerly after its closest solar pass. That does not guarantee a sequel here, but the playbook is written. Even without headlines, subtle changes carry information. The dust-to-gas ratio can shift as the energy budget evolves. Early on, volatile rich layers make gas plentiful, and dust dilute. Later, As those species deplete and the sun recedes, larger, slower grains can dominate the light. On images, that means a tail that looks broader and more diffuse, with a graceful curvature as heavier particles lag behind the comet's path. Ion features, which trace the solar wind like chalk lines in a stream, may weaken or kink as production flags, and the heliospheric breeze takes over the choreography. Photometry and polarimetry become especially useful now. The way brightness declines with increasing heliocentric distance on the outbound arc encodes how quickly different volatiles retreat. Measure the polarization of scattered light at a few phase angles, and you can infer whether the dust population has shifted toward fluffier, porous aggregates, often made in fresh outbursts, or toward older, compact grains that have survived multiple ejection reaccretion cycles near the nucleus. Post-perihelion changes in that curve are like footprints on a beach, telling you whether joggers or strollers passed by. Non-gravitational accelerations are another outbound tell. Asymmetries in outgassing impart tiny but measurable thrusts, nudging the trajectory away from the purely Keplerian arc. Dynamicalists model these with parameters that effectively say thrust along the sun-comet line, thrust perpendicular, and so on. Inbound, sunlight hits one hemisphere more strongly. Outbound, the seasons flip. If the fit to astrometry demands a different nudge after perihelion, you have indirect proof of seasonal venting and perhaps a hint of where the most active patches live. It is cartography by momentum bookkeeping. We should talk survival odds without melodrama. Small, fragile objects can disintegrate outright after perihelion if they were stitched together loosely and saturated with volatile pockets. Larger, more cohesive bodies usually soldier on, albeit battered and wearing fresh scars. If 3IATLAS is compact and modestly active, the most likely outcome is a gradual fade. Activity declines, brightness slips below the reach of most instruments, and the tail becomes memory and math. If it is a bag of gravel glued by frost, a late-season outburst or a soft split becomes more plausible. Either way, the fundamental fate is unchanged, the path is hyperbolic, the energy ledger stays positive, and no gravitational handshake in our neighborhood is strong enough to adopt it. The long goodbye is baked into the orbit. Visibility during this phase rewards persistence more than ambition. As the comet recedes, the apparent motion slows, and the coma can look surprisingly serene, even while the physics remains lively. Stacked imaging over successive nights can reveal the slow emergence of fresh shells from an outburst, the curl of dust synchrons peeling away, or the faint blue wink of an ion streamer if the solar wind lines up favorably. For professionals, narrowband filters isolate specific gases to track how the chemistry winds down. For the rest of us, the win is seeing change at all in something so far away and so transient. Philosophically, the outbound leg is the true character study. Many comets put on inbound makeup, early activity, excited press, hints of spectacle. After perihelion, the nucleus either keeps its composure or shows what stress has been simmering beneath the surface since before the first press release. For an interstellar traveler, those cracks and flares are testimony from another star's construction yard. Read at the moment when the spotlight is dimming. It is cosmic theater with a short second act, but the plot points matter. And then the curtain falls. The coma thins into the background. The tail melts into the sky's grain, and position updates become ephemeris footnotes. The object joins the faint diaspora threading between stars, carrying whatever new fractures and fresh surfaces the sun carved into it. No capture, no encore, just a patient exit into the deep field. In the final chapter, we will zoom out from this one visitor to the legacy it leaves, how a handful of careful measurements and a disciplined global campaign reshape the way we search, coordinate, and understand the next interstellar messenger that flickers at the edge of our vision. Chapter 18, Legacy. What we'll learn. The quiet triumph of 3IATLAS will not be a poster on your wall. It will be a spreadsheet that changes how we do astronomy. a coordinated global dataset, space telescopes, giant mirrors on mountaintops, small backyard rigs, and a few opportunistic spacecraft will anchor the first truly comparative models of interstellar small bodies. One-liner, today's faint smudge, tomorrow's mission pitch slide deck. Start with the scaffolding, standards. This apparition forces us to treat disparate measurements as one experiment. Photometry must be phase-corrected to a common recipe. Spectroscopy needs consistent flux calibration and slit loss accounting. Polarization angles must reference the same solar comet geometry. When data from Webb, Hubble, 10 ground observatories, and a handful of heliophysics instruments all land in the same coordinate and units system, the result is not just a paper, it is a template. The next visitor drops into a pipeline already tuned, and we waste fewer nights reinventing reductions while the target slips away. Models will feel the upgrade immediately. Dust phase functions, the curves that relate brightness to viewing angle, have been stitched together piecemeal for decades. With ATLAS observed over extreme angles from multiple vantage points, we finally pin down the ambiguity between grain size and lighting trick that sharpens radiative transfer models of comet Komet and, by extension, improves how we read unresolved debris disks around young stars. A better dust model is not academic. It is the difference between mislabeling a clump in a disk as a planet and recognizing it as forward scattered grit. Chemistry gets a similar elevation. Side-by-side infrared spectra across time let us measure how volatiles ramp and relax, mapping out sublimation fronts in a body that did not grow here. Feed that into thermal evolution codes, and you can back out layering, porosity, and the depth at which different ices hide. Those parameters are the knobs mission designers need to twist when they ask, what would a sampling harpoon meet at 10 centimeters at 1 meter? The more realistic the interior model, the fewer surprises for a future flyby, or, one day, a sample return. Dynamics, too, graduates from inference to calibration. The non-gravitational accelerations, derived from a long arc of precise astrometry, will test whether our standard rocket terms capture thrust from asymmetric outgassing in an interstellar body. If the fit demands tweaks, we update the equations that propagate these objects through the solar system. That matters because those same equations govern how survey software decides which streak on tonight's frames deserves tomorrow's follow-up. A better dynamical prior means fewer false alarms and fewer missed gems. Speaking of surveys, ATLAS's Cameo rewrites the odds board. Detection is probability multiplied by readiness. We will refine the volumetric rate of interstellar visitors by combining found with could have been found, accounting for cadence, limiting magnitude, and sky coverage. That rate folds into the business case for next-generation wide-field cameras. How deep to go, how fast to revisit, which ecliptic latitudes to give VIP treatment. It also tunes trigger thresholds. If we learn that interstellar comets are typically low contrast and slow brightening, automated pipelines can flag candidates before the internet does, and target of opportunity policies can spin up faster than rumor. A quieter legacy will live in policy and culture. The cross-planet coordination that squeezed bonus angles out of spacecraft will harden into playbooks, ephemeris brokers that speak every mission's dialect, pre-approved guest investigator, time blocks for transient phenomena, mirrored repositories where raw frames and quick-look products appear in hours, not weeks. We will also get bolder about citizen contributions. Synthetic tracking stacks from skilled amateurs will be accepted as standard ingredients in ephemeris refinement, with metadata requirements that make them plug and play rather than artisanal one-offs. When the next faint streak crosses a star jungle, the response will feel less like a scramble and more like muscle memory. Education and outreach gain tools that are, frankly, better than fireworks. Because 3IATLAS is subtle, it forces communicators to narrate method, why we align on the comet or the stars, how phase angle changes the view, what a spectrum actually says. That narrative, shared, iterated and archived, becomes the kit we reach for when the next "Is it a ship?" wave crests. The public will not just see pretty pictures, they will learn how to read them. That is a durable win. Most of all, the data will feed the Audacity gene. You can already hear future mission slides writing themselves, cross-platform detection probability curves, predicted volatile flux at practical flyby distances, dust hazard models for shielding, spin state evolution under jet talks, comm windows from off-Earth assets. A small, careful apparition can justify a big, careful mission. Interstellar chasers move from science fiction to line items when the error bars shrink and the failure modes look manageable.